Okay, we were talking about the mechanics of breathing. So just a quick review, we can see here that at the beginning of inspiration, the size of the thoracic cavity will be increasing because the diaphragm contracts. When it contracts, that means that it goes from the dome shape to the flat position, enlarging this entire cavity. Okay, as a result, the lungs expand to fill out the cavity. The lung volume then increases. If the volume increases, the pressure inside here decreases. So the atmospheric pressure, which is higher, will go in during inspiration. And the opposite happens on expiration. In this case, on expiration, the diaphragm is going to relax and return to the dome shape, reducing the size of his cavity. The volume then of the lungs decreases, the pressure increases, and the pressure will move now out, the air will move now out of the lungs. Okay, this is just showing us the same idea, okay? All right. What we want to talk about now is breathing modes, and there is also what we have to discuss then is quiet breathing and forced breathing. Okay, quiet breathing is simply the inhalation. During the inhalation phase, the muscular contractions of the diaphragm, mostly for the most part, and also what we call the inspiratory muscles. The inspiratory muscles are the external intercostals, okay? So these are involved then with quiet breathing. So you have the contraction of the external intercostals, and those muscles lift the rib cage and pull the sternum forward. It actually flares out the sternum. So this helps the size of the volume of the lungs to increase, okay? On quiet breathing with exhalation, okay, exhalation, this is mainly a passive process due to the elasticity of the lungs themselves. The inspiratory muscles relax actually, and this helps the rib cage descend and the lungs recoil, okay? So remember that the inspiratory muscles are called the external intercostals. It's kind of a opposites with meaning the same thing. So inspiration muscles are taken care of by external intercostals. With forced breathing, oh, and one other thing I wanted to mention, that the with exhalation, with quiet exhalation, the passive process, the phrenic nerve has an important role in the expiratory cycle. But anyway, with forced breathing, and forced breathing or forced expiration is going to be the is going to happen with both inhalation and with exhalation, and both of these processes are now going to be active. Okay. Now, when would forced breathing occur? Well, this would occur, for example, in a pregnant woman. The uterus is enlarged and it pushes onto the abdominal organs. They in turn push up against the diaphragm. So the woman needs to use the rib cage to breathe towards the end of pregnancy. Now, during this forced inhalation and exhalation, these active processes, the inspiratory accessory muscles are involved. What do we mean by the inspiratory accessory muscles? Well, these are the sternocleidomastoid, the scalenes, and these are both for inspired, or these are both for labored inspiration. So forced expiration, we have the contraction of the abdominal wall muscles, and this includes the oblique and the transversus, okay? And that increases the pressure in the lungs, which is going to force the abdominal organs up against the diaphragm, and it's going to depress the rib cage, so the volume in the lungs will decrease, okay? So forced expiration then is going to involve the abdominal wall muscles, that is the oblique and the transversus, and the inspiratory muscles for forced breathing are going to be the sternocleidomastoid and the scalenes. So we can look at that here. During normal quiet inspiration, okay, this is the first case, the diaphragm and the external intercostal muscles contract, okay? And remember, the external intercostal muscles are the inspiratory muscles, okay? And then during labored inspiration of the sternocleidomastoid and the scalenes, for the most part, also contract, okay? Now, during normal quiet expiration, the diaphragm and the external intercostals, okay, the diaphragm and the external intercostals are going to relax. But during labored expiration, the abdominal and the internal intercostal muscles contract, okay? So you can see here the inspiratory muscles, okay? The inspiratory muscles for quiet breathing are the external intercostals, which are being shown here. For forced inspiration, we have the sternocleidomastoid and the scalenes. There's the sternocleidomastoid, which you're very familiar with, and the scalenes. Okay, the diaphragm is also for quiet inspiration, okay? And the forced expiration, we can see here that we have checked off the internal abdominal oblique and the transversus abdominis, okay? Okay, so that takes care of the quiet breathing and the forced breathing. Okay, before we get to this though, whoops. All right, what is artificial respiration? Well, this is when air is administered to an individual whose respiratory muscles no longer work. When would something like this happen? Well, this doesn't really happen quite as often as it used to, but even in the 40s and 50s, you had severe cases of tuberculosis. Tuberculosis is basically in our country diminished, although cases of it are popping up. But it used to be so bad that eventually it was a disease that affected the lungs and caused terrible necrotic damage, and people could not breathe. So they came up with these iron lungs. They were chambers in which people would have to lay in order to breathe. Okay, it was a horrendous situation, and it was the only way they could live. And there were sanitariums built for this purpose. These are no longer in existence, thank goodness. But anyway, if we have to administer air to an individual, if the respiratory muscles are not working, then we can use mouth-to-mouth resuscitation, and the rescuer in this case exhales once into the mouth of the victim. Now, even though we think of exhalation as giving off CO2, there's enough oxygen in a normal person's exhalation to give to the victim, okay? And then we break from doing that, okay? After we give the exhalation into the person's mouth, we break away and we break contact to allow the victim to exhale, which we know is a passive process. So there'll be passive exhalation, and the victim hopefully gets enough oxygen during this process. An endotracheal tube can be inserted into the trachea through the glottis, and at the other end, we connect a mechanical ventilator. So we no longer need the iron lungs. Okay, we want to talk about the respiratory volumes, and the respiratory volumes are very important because they measure the individual's lung capacity. So we have the tidal volume. The tidal volume is the amount of air that's moved in or out of the lungs during one respiratory cycle at rest. And that amount is about half a liter, okay? This is the tidal volume. You can see this labeled over here in the graph, okay? It's about half a liter. And this is, again, the amount of air moved in or out of the lungs during one respiratory cycle at rest. We also have the expiratory reserve volume, okay? The expiratory reserve volume, or the ERV. This is the amount of air that could be voluntarily and forced to be expelled. In other words, what we can voluntarily force out. And this is about a liter, okay? So you can see that here, the ERV is about 1 liter, okay? Then we have the inspiratory reserve volume. Okay, in other words, the amount of air taken in over and above the tidal volume. Okay, it's 1 o'clock now. It's the afternoon. It's not at night. I stopped last night. It's 1 o'clock. It's the next day. Just so those of you who are keeping track of how long I'm doing this for. But anyway, the inspiratory reserve volume, the amount of air it's the amount of air taken in over and above the tidal volume. So it's the amount of air that can be inspired forcibly beyond the tidal volume. And the IRV in men is about 3.3 liters, and in women it's about 1.9, almost 2 liters, or 1900 milliliters. So you can see that over here, the inspiratory reserve volume is, they're giving sort of an average of 3.1 liters, or 3,100 milliliters, okay? So then if we add up the tidal volume plus the IRV and the ERV, that is called the vital capacity. That is the maximum amount of air that can be moved in and out with forced breathing in a single cycle. Okay, this is with forced breathing because remember, we're doing forced inspiration and forced exhalation, and that is going to be the vital capacity. The residual volume, okay, is the amount of air that always remains in the passageways and the alveoli. This air cannot be expelled even after forced exhalation. It's the amount of air that always stays in the passageways and the alveoli, and you can see that that amount for the residual volume is about 1.2 liters, or 1,200 milliliters. So we can come up with another total called the total lung capacity, which includes this residual volume. So it's the total lung capacity is really going to be the residual volume included into the calculation of vital capacity. Remember, vital capacity was IRV, ERV plus TD, and now if we just add on the reserve volume, the residual volume rather, we have the total lung capacity. We also have dead space. Dead space is the amount of air that never gets into the respiratory system. It's the volume of air that's in the conducting passages, in the pharynx, the larynx, the trachea, and the primibronchi. If the tidal volume is 500 mils, which we said, a half a liter, the first 350 mils goes through the passageways and enters the alveolar spaces. But the last 150 mils never gets past the conducting passageways, and this is what we mean by the dead space. So even though the tidal volume is a half a liter, only 350 milliliters really goes through the passageways and enters the alveolar spaces, okay? And pulmonary function tests are used to monitor several aspects of respiration and diagnose conditions, for example, like asthma. And they use a device called the spirometer to measure things like the vital capacity, the ERV, and the IRV. And you can see that all of this can be nicely graphed. We can see here what's going on, and we can make recordings with a device called a spirometer. Okay, here's another diagram, the same thing, okay? All right, next we want to move on to gas exchange. Okay, in other words, we want to see what goes on at the level of the pulmonary capillary, which is the respiratory membrane, and we want to see what goes on with the systemic capillaries. So we have to realize that we're talking about two different areas. Diffusion across the respiratory membrane is when you have air from the alveoli bringing in oxygen to the blood, okay, and the carbon dioxide from the blood is going to the alveoli to be expelled with the air. This is going on across the respiratory membrane. Now, the oxygen that comes in through the alveoli from the air to the blood goes to the systemic circulation, and then it goes to the interstitial fluids, okay, the interstitial spaces, the tissue spaces. On the other hand, from the interstitial fluid, the CO2 is going to be taken out through the blood, the same the venous blood, and is going to be brought back to the lungs to be expelled. Now, these exchanges depend on the partial pressure of the individual gases. So we want to look at the diffusion of the molecules, and we want to look at the partial pressure of the gases. Now, the normal composition of air, okay, is going to have 78.6% of nitrogen, 20.8% of oxygen, 0.5% of water, and 0.04% of CO2. Now, the pressure at atmospheric level, at sea level, is 760 millimeters of mercury, and that equals 1 atm. So each of these gases contributes to this total pressure of 1 atmosphere, or 760 millimeters of mercury, these different percentages. The partial pressures that are contributed by a single gas will determine the rate of diffusion across a membrane for the individual gas. For example, the partial pressure of oxygen determines how much oxygen enters into solution, but the partial pressure of oxygen has no effect on the diffusion rate of the other gases. Now, we can figure out the partial pressure for oxygen and see what its contribution is to this 1 atmosphere by simply taking 20.8% and turning that into a decimal, which is 0.208, multiply that by 760 millimeters of mercury, and we get the partial pressure for the oxygen to be 158 millimeters of mercury. Or for carbon dioxide, it's 0.3 millimeters of mercury. So we can do those calculations. Now, if you recall Dalton's law, it's the total pressure of a gas mixture is equal to the sum of the partial pressures of each individual gas that contributes towards the total. And so I just used that actually to calculate the partial pressure, as you just saw, for oxygen, which is 150 millimeters of mercury, 158 rather, and for carbon dioxide, it's 0.3 millimeters of mercury. So I can figure out the partial pressure based on the atmospheric pressure for each one of these gases, for nitrogen, oxygen, water, and CO2. Let's calculate the partial pressure of nitrogen. So again, what we would do to do this, we would take the percentage of nitrogen, which is 78.6%, turn that into decimal talk, and that would be 0.786, multiply that by 760 millimeters of mercury, the total pressure, and I would see that the contribution that nitrogen makes, or the partial pressure of nitrogen in the atmospheric pressure, is 597 millimeters of mercury. This is a very high partial pressure, so nitrogen will diffuse very rapidly. This explains decompression sickness, or the bends. If the scuba diver returns to the surface too quickly, the pressure decreases suddenly. So nitrogen will come out of solution and start to form bubbles. In other words, under pressure, the nitrogen is in solution. But as the pressure decreases suddenly, it comes out of solution, it forms bubbles. These bubbles occur in the joint cavities, in the bloodstream, and the cerebral spinal fluid. And this is very painful. It causes the person to curl up, and this is commonly called the bends. This can also occur if the cabin pressure in an airplane suddenly decreases. That's why they immediately drop the oxygen masks. Emphysema, okay, is worth discussing. It's when the alveoli walls, or the surfaces of them, are disrupted, and they're destroyed so that the alveoli merge with adjacent alveoli, forming a large non-functional airspace. In other words, the surface area for O2 and CO2 exchanged is greatly diminished. The symptoms are shortness of breath. Shortness of breath is called dyspnea, which also means difficulty with breathing. So there's an inability to tolerate physical exertion when you have emphysema. The causes are inhalation of cigarette smoke due to the toxic vapor and particles inside of cigarette smoke. There's also a genetic predisposition for getting emphysema, and it is a normal consequence of aging. Okay, we'd like to talk about gas transport now, and we'll take a short break first, and then we'll go back into gas transport.